In this video, we're going to talk about the Cartesian equation of a line. We'll start with this statement. If the slope of a line is b over a, then the direction vector is ab. Well, here's an explanation. If the slope of a line is b over a, then that means rise over run is b over a. Now, some people learn delta y over delta x is b over a, and some people maybe instead learn y2 minus y1 over x2 minus x1 equals b over a. Now, however you learn that, the increase in the x coordinate from one point to the other is a. It's the denominator. So x will increase by a. At the same time that the increase in the y coordinate from one point to the other is b, so y will increase by b. Another way of saying that is to get from one point to the other, we'll follow the vector ab. X will increase by a and y will increase by b. And so what we can then get is this statement: if the slope of a line is b over a, then the direction vector is ab. And it works if it's negative as well. I was assuming them to be positive for my little explanation, but it works still if we have negative values for b and or a. So we have a nice little rule that we're going to remember moving forward. Another rule is that if the Cartesian equation of a line, or what's sometimes called standard form equation of a line, is ax plus by plus c equals 0, then the slope of the line will be negative a over b. Well, how do we show that? This one's pretty easy, I think. All we do is we take that equation of the line and we're just going to isolate b. So we're going to move ax and move c, and we'll get this equation here. Now we're going to divide everything by b to get a new equation where y is isolated. And what we can then do is just say that that's the same as saying negative ax over b minus c over b, which is another way of saying negative a over b times x and then minus c over b. And if that was true, we would see our slope would be negative a over b. So we get that statement. So we have a nice little statement at the top, and we'll remember this one as well as the first one that we talked about. Now, if ax plus by plus c equals 0, then the normal vector is ab. You might be wondering, what does that mean? Well, the normal vector refers to the direction vector of a perpendicular line. So normal in this context means perpendicular. So here's our explanation. We already showed that if ax plus by plus c equals 0, then the slope of the line will be negative a over b. Well, that means the slope of a perpendicular line would be b over a, the negative reciprocal. Okay, well, that would mean that the rise would be b and the run would be a. So for every increase of a, there would be an increase of b. Could be a decrease as well. A or b could be negative as well here. So the direction vector of the perpendicular line would be simply ab, meaning and that's exactly what a normal vector is. So the normal vector is ab because the slope of a perpendicular the normal vector is ab because the direction vector of a perpendicular line is ab. And so that gives us this statement up here. Okay? Again, normal essentially means perpendicular. So let's do a few examples using these principles. Determine the equivalent vector and parametric equations of the line y equals 3/4 x plus 2. Well, we know from grade 9 math that the y-intercept of the line is 0, 2. If you don't know that, if maybe you don't remember that that's the y-intercept of the line, another way of, you need to come up with a point on the line. So another way of doing that would just be let x equal 0. Build yourself a little table of values, let x equal 0. That would mean y would be 3/4 times 0 plus 2, so y would be 2. So in other words, a point on the line is 0, 2. We know to come up with a vector equation that we need a point on the line. So the point is 0, 2, meaning we could use the vector 0, 2 to get us in position on the line, i.e. be a position vector. But if you don't have to do all that table of values stuff and you just simply remember that when you have it in y equals mx plus b form, b is the y coordinate, that's helpful, saves you a few seconds. Anyways, however you do it, to get the vector equation of a line, we need a point on the line so that we can establish a position vector. And it's pretty easy to see one of the points on the line will be 0, 2. So we're going to use the vector 0, 2 as our position vector. Now we go into an explanation here, very similar to what I just finished saying. Now we also need to find a direction vector. Well, one of the first things we said here is that if the slope of a line is b over a, then a direction vector is ab. So in that case, letting the slope of the line be b over a, we say b is 3 and a is 4, meaning the direction vector is ab, which is 4, 3. And so we can say that right there. Our direction vector is 4, 3. Our position vector is 0, 2. So a vector equation of the line is r equals 0, 2 plus t times 4, 3. T is an element of the reals. Now the parametric equations would be x would be equal to 0 plus 4 times t, or we can simply say x equals 4t, and y would be 2 plus t times 3, or in other words, y equals 2 plus 3t. And again, t has to be an element of the reals. Now, given the line r equals 3, 6 plus, there should be a vector there, r equals 3, 6 plus s times negative 1, negative 4, we're going to determine the equivalent slope y-intercept form and the Cartesian equation. So, what we'll do, since the direction vector is negative 1, negative 4, I seem to have lost my pen there. Since the direction vector is negative 1, negative 4, we know the slope is negative 4 over negative 1, which is another way of just saying 4. So we know we can say y equals 4x plus b. And then we'll just sub in the point 3, negative 6. And if we do that and solve for b, we get that b is actually equal to negative 18. And so we can say that the slope y-intercept form of the line is y equals 4x minus 18. Now let's find the Cartesian equation. Well, since the direction vector of the line is negative 1, negative 4, that means the normal vector is 4, negative 1. That's one of the rules on the slides that we talked about earlier. Well, if the normal vector is 4, negative 1, and all we did there was we just switched x and y. We switched their positions, and then akin to a negative reciprocal, what we did is we changed the sign of one of them. So we switched the position of the negative 1 and the negative 4, but in grade 9, you learn that for a perpendicular line, you want the negative reciprocal, which means you change the sign of either the numerator or the denominator. So in a similar way, you're just changing the sign of one of those two values. So we get 4, negative 1. Now, if we consider the normal vector to be 4, negative 1, then we know one of our rules tells us that the Cartesian equation of the line will be 4x minus 1y plus c equals 0. Now we want to solve for c, and like we learned in grade 9, we sub in any point on the line, so we'll use the point 3, negative 6. And if we do that, ultimately solving for c, we get that c is negative 18, and we can say the Cartesian equation of the line is 4x minus y minus 18 equals 0. Now let's determine the Cartesian equation of a line passing through the point 4, negative 2 that has the vector 5, 3 as its normal. Well, since the normal vector is 5, 3, then the Cartesian equation of the line will be 5x plus 3y plus c equals 0. It's a really user-friendly formula. Now we'll sub in a point, and specifically we know the line passes through 4, negative 2. Subbing that in, we get c equals negative 14, and we can say that the Cartesian equation of the line is 5x plus 3y minus 14 equals 0. Now Next question. For what value of k are the lines kx plus 4y minus 4 equals 0 and 3x minus 2y minus 3 equals 0 perpendicular? Well, right away we can say that the normal of the first line is k4 and the normal of the second line is 3, negative 2. Now, an interesting fact, it'll take a little bit of thinking, but I think you'll get it pretty quickly, is that in R2, if two lines are perpendicular with each other, then their normals are perpendicular with each other as well. So just imagine it. Imagine we're in R2, and we've got these two perpendicular lines that I'm drawing in red right there. Okay, we got a 90-degree angle there. Now imagine, if you will, if we drew a line perpendicular to each of them. So if I draw a line perpendicular to this vector, if I draw a vector perpendicular to that line, I'll get a vector that looks something like this. Then look at the next line. If I draw a vector perpendicular to it, I'll get a vector that looks like this. Well, those vectors are perpendicular with each other. So if two lines are perpendicular, then the normal of one line is perpendicular to the normal of the other line. That's pretty cool. So we come up with the statement said right there. So now I'm repeating myself. If two lines in R2 are perpendicular to each other, then their normal vectors will be perpendicular to each other. And so then, and a more general statement actually that'll be useful as well, is that the angle between the normal vectors of two lines actually equals the angles between the lines themselves. It doesn't just have to be a 90-degree thing, but that's also an interesting rule that'll come up later. But to come back to this question, we basically want to solve for k so the normal vectors are perpendicular, thereby making the lines themselves perpendicular. And if the normal vectors are perpendicular, that means their dot product should equal 0. So really all this question becomes is determine the dot product of those two vectors and set it equal to 0 and solve for k. So we see here that k times 3 plus 4 times negative 2 needs to equal 0. So 3k minus 8 equals 0. K needs to equal 8/3. Now let's determine the acute angle formed at the intersection of this pair of lines. Well, recall from grade 9 that any two lines in R2 that are not parallel will intersect each other at exactly one point. Well, these two lines are definitely not parallel because the direction vector of one of them is negative 1, 3, and the direction vector of the other is 3, 4. Those are not scalar multiples of each other, so the lines are not parallel. Okay, so therefore these lines will intersect at one point. And the angle of intersection of the two lines will be equal to the angle of intersection between the two direction vectors. So all we have to do is determine the angle of intersection between those two direction vectors. Pretty straightforward dot product question. Negative 1, 3 dotted with 3, 4 is equal to the magnitude of negative 1, 3 times the magnitude of 3, 4 times the cos of theta. We plug in some numbers and get to work. And what we end up with is that theta ends up roughly equaling 55.3 degrees. I'll let you look at the numbers there if you'd like. Now, try to remember also that if two lines meet at an acute angle, that means there's also an obtuse angle there. This word here should be obtuse. Okay? So you can see that drawn in your diagram. If we've got this acute angle, well, there's also 180 degrees minus that acute angle will give us an obtuse angle. So in this case, the acute angle is approximately 55.3 degrees, and the obtuse angle is approximately 126.7. Now, this question actually only asks for the acute angle, so our final answer will be 55.3 degrees. In this question, we want to determine the acute and obtuse angle between these two lines. So, like we said earlier, the angle between two lines in R2 will be equal to the angle between the normal vector of the first line and the normal vector of the second line. The normal vector of the first line is 3, negative 2. The normal vector of the second line is 1, 4. We just need to figure out the angle between those two vectors. So doing that, normal 1 dotted with normal 2 is equal to the magnitude of normal 1 times the magnitude of normal 2 times cos theta. Plugging in a few numbers, we ultimately get that theta is roughly equal to 109.7 degrees. Well, if two lines meet at an obtuse angle of 109.7, something like this, they're also meeting at an acute angle of 180 minus 109.7, which is this. Again, we're not talking about two vectors, which must be tail to tail. We're talking about two lines. So there are two possibilities here. The acute angle between the lines is approximately 70.3 degrees, and the obtuse angle between the lines is approximately 109.7 degrees. Now for this last question, this is kind of challenging. The line segment joining the point 20 with the point 53 is the hypotenuse of a right triangle, and the third vertex of that triangle lies somewhere on the line 3, 1 plus t times 1, negative 2. We want to determine the coordinates of C. So just to sort of show you what's going on here, imagine we see the point 20, which is right about there, and we see the point 53, which is right about there. There's your A and there's your B. Now, we've also got a line 3, 1, and plus a direction vector of 1, negative 2. And so what we've got is a we know that there's going to be that we know we've got a hypotenuse here, but we've also got a point somewhere on AB where if we put the point there, we're going to get a right angle triangle. So we might even be able to picture it could be right about here. Put a point there, and we see, hey, yeah, we can actually make kind of a right angle triangle there. That'll be the answer. But what this question's trying to get through to us is there actually might be more than one answer, because maybe you could build your triangle the other way. You got a right angle there, and so maybe that point down there is the answer. So there could be more than one answer here, but either way, what we're trying to do is find the coordinates of that point right there. How are we going to do such a thing? Well, dot product. We know there's a right angle at point C, so that means the vector AC will be perpendicular to the vector BC. So again, just going back here for a second, let's look at this, let's redraw our diagram just for a moment, and we've got A and B are a line right there, and we've got a line going through here. So let's just focus for a minute on this first situation here. Now, if this is point C right there, we got A and B. If that's point C, then what we're trying to say here is that, what we're trying to say here is that the vector AC will be perpendicular to the vector BC. So going back to our diagram, the vector AC will be perpendicular to the vector BC, therefore putting a right angle here, therefore making this a hypotenuse of a right angle triangle. So AC is perpendicular to BC is what we're trying to get through. Now, we know that C is on the line R equals 3, 1 plus T times 1, negative 2. It says it right there. Okay? Well, what that tells us, every point on that line satisfies the parametric equation x is 3 plus 1t. And it also satisfies the parametric equation y is 1 minus 2t, right there. Okay? So we know that the coordinates of point C will be 3 plus t, comma 1 minus 2t. Okay? So that means that the vector AC, or it's worth writing that one more time, C is the point 3 plus t, comma 1 minus 2t, because literally every point on that line has those coordinates. So if we want to get the vector AC, well, the vector AC will be the vector, we'll just subtract the x components backwards. 3 plus t minus 2 ultimately equals t plus 1, and 1 minus 2t minus 0 ultimately equals 1 minus 2t. That'll be the vector AC, the vector that goes from that point to the point 3 plus t, 1 minus 2t. And if that didn't quite make sense, pay attention one more time. We'll do it again. The vector BC will be the vector that goes from the point B to the point C. Well, in order to determine that vector, we subtract the x-coordinate of C minus the x-coordinate of B. 3 plus t minus 5 ultimately will be t minus 2, and 1 minus 2t minus 3 ultimately will be the point negative 2 minus 2t. So there's your vector BC. All of this is written right here for you. So AC will ultimately be the vector t plus 1 comma negative 2t plus 1, and BC will ultimately be the vector t minus 2 comma negative 2t minus 2. Since we said earlier the vector AC is perpendicular to the vector BC, we know AC dotted with BC will equal 0. So we just have to dot those two vectors that I have circled right there. So dotting them and setting it equal to 0, we get t plus 1 times t minus 2 plus negative 2t plus 1 times negative 2t minus 2 is equal to 0. Expanding and expanding, we get this long equation here. We're going to collect like terms, and when we do that, we're going to get 5t squared plus t minus 4 equals 0. We can factor and solve that. 5t minus 4 quantity times t plus 1 quantity equals 0. So that means t will be 4/5 or t will equal negative 1. Now keep in mind again, we've been saying for a couple of slides here that c is representing the point 3 plus t, comma, 1 minus 2t. So in order to get the coordinates of point C, we'll let t be 4/5 and plug it in for both. And then we'll let t be negative 1 and plug it in for both. And we'll get a couple of different points. So t equaling 4/5 means that the coordinates of point C will be 19/5 comma negative 3/5. Or t equaling negative 1 means that the coordinates of point C will be 2, 3. Which means we've got a couple of different answers possible here.